Welcome to chapter 13.3. Now, this section is about conservative vector fields, fundamental theorem for line integrals, and path independence. Now, in the previous two sections, we talked about vector fields, and then we even talked about the line integral of vector fields. Now, in this section, we study a special type of vector field called a conservative vector field. And we defined a conservative vector field in the following way. So, a conservative definition, conservative vector field. A vector field F we have a vector field F on a region is called conservative if it is the gradient of a scalar function, little f. So in other words, a vector field f is conservative if we can find a scalar function little f such that gradient of little f equals to the given vector field. Now we have a special name for this scalar function, and we call this function as the scalar potential function. Okay. Now, this is the way we defined a conservative vector field. Again, a vector field f is conservative if it is the gradient of a scalar function. And so if I recall the gradient of f, okay, so let's recall in three-dimensional space, gradient of f equals to partial over partial x of little f. This should be a vector, partial f over partial y and partial little f over partial c. Okay. So if you can find a scalar potential function little f so that its gradient equals to the given vector field, it means your vector field f is a conservative vector field. Let's consider a very simple example. So we want to verify the vector field. Verify the vector field f equals to 2xy comma x squared is conservative with the scalar potential function little f equals to f of x comma y equals to x squared y. Okay. So let's calculate the gradient of little f. So we have partial over partial x of f comma partial f over partial y. But what is my little f? Little f is x squared y Now if you take the derivative of the first one with respect to the x variable, you will get 2xy comma partial y of x squared y is nothing but x squared, and now we see that this gradient of scalar potential function equals to the given vector field, equals to the vector field f. So yes, our vector field f is conservative. F is conservative with little f equals to x squared y. Again, gradient of little f equals to the given vector field. Therefore, our vector field f is conservative. So next, we want to discuss about the test that we can use to test these vector fields are conservative or not.